Hi everyone, welcome to this presentation of CO2 Refrigeration and Heat Pumping System. I am Shailen Kasera from Ashir Rajasthan Chapter. I welcome Mr. Greg Shivner, Ashir Distinguished Lecturer. Today as a refrigeration activity, we Rajasthan Chapter, Western India Chapter and Chandigarh Chapter are jointly organizing this virtual DL presentation on CO2 refrigeration and heat pumping system. I would like to read the Ashley Code of Ethics. In this and all other Ashley meetings, we will act with honesty, fairness, courtesy, competentness, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflicts of interest. So actually founded in 1894, is a global society advancing human well-being through sustainable technology for the built environment. The society and its members focus on building systems, energy efficiency, indoor air quality, refrigeration, and sustainability within the industry. Through research, standards writing, publishing, and continued education, Asia shapes tomorrow's built environment today. Asia is celebrating 125 years of shaping the built environment. Become a member of Asia by visiting ashray.org/join. Mr. Jake Shavina started in the refrigeration industry as an apprentice refrigeration mechanic in 1997 and completed his journey person certification in 2003 with an award for most outstanding new journey person. Continuing to work in the refrigeration industry, Jake completed a BSc in mechanical engineering with distinction from the University of Saskatchewan in 2011. Having worked in roles from all the way from mechanic to design engineer, Jake can offer a comprehensive viewpoint on refrigeration related construction and design. In 2014, he founded Core Dynamics, which merged with Laporte Engineering in 2019. And he now involved with refrigeration consulting work, including design, inspection, commissioning, advanced troubleshooting, energy auditing, control sequence optimization, and training. Coupled with a passion for energy efficiency and the environment, this unique experience leads to an in-depth understanding of the parameters affecting efficient refrigeration system operation. Thank you, Mr. Great profile. Now, CO2 refrigeration and heat pump. The use of CO2 as a refrigerant has grown in the residential and commercial and heat pumping industry. This presentation will explore the different applications that have used CO2 and will examine its efficiency as a refrigerant in different conditions. While reviewing subcritical and transcritical operation of a CO2 refrigeration cycle, we will dispel myths about the efficiency of CO2 and understand which applications are best suited for its use as a refrigerant. Now here we have some instructions for the participants. Participants can post their queries with question panel. So Mr. Greg will answer after the presentation. You can also download the presentation from the handout. This webinar will be recorded and uploaded to YouTube channel of Rajasthan Chapter and Raj Chapter also. Please do not forget to fill the webinar evaluation form. It will come up when you end the webinar. You will also get a certificate after 3 hours from this presentation. Now I invite Mr. Greg to present much of it webinar. Already 175 personnel joined. So I am sharing the screen.
Okay, which?
Yeah, your screen is visible.
Which screen are you seeing? Sorry.
Both screens, CO2 refrigeration and one another slide is also here. Next slide is also.
Okay. Okay. Okay, so you should see the screen properly. Just give me 1 second here. So yeah, so thank you, thank you everyone for having me today to talk about CO2 refrigeration and heat pumping. This presentation is a presentation that was part of the distinguished lecturer presentations that I had put together for the last couple of years for ASHRAE, and sort of unfortunately last year I changed the presentation to be more interactive and more I guess more interactive and more engaging for people in a live audience, because that's where I was doing it. And now with COVID, unfortunately, we're doing a lot more web-based webinars. So you'll hear me talking a lot on most of the slides. So I guess I'll just give me 1 second here. How come it's not going? There we go. So one of the things that
you can maximize your slide.
Yeah, you should be seeing. Okay, just give me a second here. It says you're seeing screen 2. There we go. Let's do that. Is that better?
Yeah, it's better now. Yeah, yes, you can.
Okay, sorry about that. It had my screens numbered funny, but it's good. I got it. Okay, so let's go there. So yeah, so thank you for having me, and I just want to we'll go through and talk a lot about CO2. So I've given this presentation several times to ASHRAE chapters throughout North America, and so I guess I have to, in advance, just a bit of a fair warning. I work a lot in Fahrenheit and in imperial units, so if that's an issue, I guess just bear with me. Yeah, so we've got one of the things that's happened lately is a kind of a resurgence of CO2 being used as a refrigerant, and so I wanted to spend a little bit of time talking about the history of CO2. I think that's important. When I started as a refrigeration mechanic in the 1990s, CO2 wasn't used anywhere in North America of any significance, other than in, of course, like CO2 production facilities and things like that from a refrigeration standpoint. And but it started showing up in Europe, and we talked about it as a new technology, but it's kind of important to understand that it isn't really new. The gentleman that you're seeing on the screen right now, his name is Alexander Twining. He patented a CO2 refrigeration system in 1850. I don't know if he was the only one around that time, but he had started using and patenting CO2 refrigeration system, and he was one of the things that I find really interesting when we go back in time is the kind of the breadth of research and disciplines that a lot of the engineers of the day were involved in. Alexander Twining was a civil engineer who worked in the railroads in the northeastern United States, and he went on from working on railway and then CO2 refrigeration systems to becoming a professor of astronomy, math, and physics, and I actually believe like a priest or something as well. And he has done original research in the theory of radiation on meteor tracks and different things like that. So hence the star picture there to the right. But I always find that really interesting. So CO2 had been used in the U.S. in any case in the late 1800s and early 1900s, but by about 1930, it had fallen out of favor from some of the other refrigerants. So mainly ammonia in industrial applications and halocarbons of some description. So CFCs, typically R12 was invented in, I think, 1928. And so it had fallen out of favor, and for probably good reason. So we're going to talk a lot about the challenges of CO2 today, and we'll learn that there's some things about it that make it fairly challenging to use. So it kind of fell out of favor, and it started seeing a bit of a resurgence in research in Europe in the 1990s and early 2000s. and of course has gone significantly improved, or not improved, significantly more applications and installations since then. So why are we talking about CO2 again, and why did it get a bit of a resurgence? So as most people know, but not everybody, so I'll spend a minute here. We've gone through a lot of refrigerant changes since the 1980s, and this isn't a presentation on the Montreal Protocol or the phase out of CFCs, but that's essentially what led to the discussion and the importance of considering refrigerants like CO2 as alternatives to what was being used. So in the 1980s, we began a phase out of CFC refrigerants. I know that obviously different countries were on different schedules. Our phase out of CFCs finished in the, I think, late 1990s, early 2000s in Canada anyway. And one of the things that happened as we transitioned from CFCs, so CFCs have chlorine in them, they're damaging to the ozone layer, and so it was very important that we phase those out. However, one of the things that happened as we phased those out, we transitioned to HCFC blends, so hydrochlorofluorocarbon blends, like our 409A, I think is one, and they had different names, MP39. I think 409A might not be one actually, but anyways, there's several different blends we transitioned to while HFCs were being developed, hydrofluorocarbons or halofluorocarbons. And so they were refrigerants like R507, R410A, R404A. All of these refrigerants are more or less ubiquitous in North America and used throughout the world everywhere, and we're in Europe as well. And so one of the challenges arose though, because while we were working on a problem to reduce ozone, the destruction of the ozone layer, a lot of these new refrigerants remained fairly high in global warming potential. And in the 1990s and early 2000s, this was recognized as kind of a problem that was going to need to be addressed. And we're seeing today more and more action with the phase down of a lot of these refrigerants. So R507 in Europe is part of the F-gas regulations. It's being phased down in Canada and the US. We've got similar things. Several states and several countries have agreed to the Kigali Amendment to the Montreal Protocol, which phases down the use of HFCs. So this chart that you're looking at shows you a little bit of a map of some of the refrigerants. On the top, we were using R22. It's an HCFC. It's being phased out, or is phased out in many places. We've got 410A, which is the main refrigeration air conditioning refrigerant that's in use in most places, or was, and 507, which is one of the most common refrigerants for commercial refrigeration applications. 134A is obviously popular, and those numbers that you're looking at are the GWP, the global warming potential. So as we transition lower and lower, for lower and lower global warming potential, we start running into challenges with materials. We have refrigerants like R1234YF, which has a very low global warming potential. It's being used in a lot of vehicles now, but it's flammable. And again, this isn't a presentation on flammable refrigerants either, but that adds to some challenges when it starts being applied to certain applications. Propane is low as well, R290, and right near the bottom, just by definition, the global warming potential of CO2 or carbon dioxide is 1. And so that's starting to get attention because it's one of the only refrigerants that's down there that receives an A toxicity rating from ASHRAE and a 1 flammability rating. So it's an A1 refrigerant. Ammonia is toxic and also slightly flammable, and other refrigerants like R1234YF are non-toxic or low toxicity, but also slightly flammable. So this is why carbon dioxide has been and CO2 has been brought up and is becoming more and more popular. But it has a lot of challenges, and it has a lot of things about it that are really, really interesting. So one, I guess we'll spend a bit of time just going through really briefly the challenges and talking about some of them. So one of the challenges is this is the part of the presentation I usually have a large audience interaction with, so I apologize, I stumble a little bit. So one of the challenges with CO2 is high pressure. The pressures of CO2 when we are working on a refrigeration system, if you know what typical pressures are for, say, for example, R12 used to be 30 psi suction pressure and 150 psi discharge pressure, in that range, similar to ammonia. Our 507 is higher, 410A is even higher than that, with discharge pressures of like 450 or 500, and suction pressures of around 150 or so for an air conditioning type application. And with CO2, we are in the range of and just so I guess, again, I'm not familiar with units that everybody, but 150 psi is about 10.5 bar or so. With CO2, we are looking at pressures in the 500 to 600 psi range, so 35 bar for the suction side, and up to 110 bar or 1600 psi on the discharge and condensing side of things. So significantly increased pressure to operate certain types of CO2 refrigeration systems, and we're going to talk about the different types right away. So high pressures were one thing that made it a little bit difficult to use. High pressure is not so hard to deal with in small components. So if you're into machine design or into pipe stress and things like that, you know that with a relatively thin wall, even 3/8 tubing can hold. For example, it's fairly easy to build small tubing to hold 1500 psi. But as components get larger, the high pressure ratings become a lot more challenging and a lot more expensive to handle. The other thing that CO2 has that's a challenge is it has a phase change to solid that happens within the pressure region, the pressure realm you could see in your refrigeration system. So none of the other refrigerants have this property. And CO2 has a phase change to solid at around 80 psi. Regrettably, I don't have the exact number written down here, but I'll show you a phase diagram right away. And CO2 changes to a solid as it transitions from a vapor as the pressure decreases in certain places on the phase diagram. So this is a problem in the case of, for example, reliefs. So when a pressure relief valve opens, we could have a transition from vapor to solid or saturated vapor to solid. So we're going to talk about that in the safety section of the presentation near the end. The other major challenge that CO2 had and has is the supercritical cycle, which again we'll talk about that terminology momentarily. The supercritical cycle is not very energy efficient in a lot of applications, and in particular in warm climates. So we're going to talk we're going to work through now a couple different refrigeration systems or types of systems that use CO2 and see how those challenges can be addressed in different ways. So first, just for those of you who are interested, this is the approximate phase diagram of CO2, showing that there's a solid point that happens in the pressure regions that we're used to. So when you have a depressurization of a CO2 refrigeration system, you can end up with solid in your piping, for example. That happens at about 76 psi and minus 70 Fahrenheit. So again, apologies on the Fahrenheit. So one of the things that we need to do and to talk about CO2 and to understand, we mentioned it has some challenges, it also has some benefits, so we're going to talk about that. One of the things that we need to do is talk about pressure enthalpy diagrams. So this is a pressure enthalpy diagram. So for those of you who aren't familiar, I'll give you a really quick tour around here. So pressure enthalpy diagrams are used to look at phase changes of materials. They're particularly useful when talking about the refrigeration cycle, and I'll show you why momentarily. So just to give you a bit of a tour around, so a pressure enthalpy diagram is basically a chart that has pressure on the y-axis. So lines of constant pressure are the purple lines that go horizontal on the diagram. Lines of constant enthalpy are vertical on the diagram, so enthalpy is the x-axis. So those are the two main properties that we show. And then from here we've got this black dome showing on the diagram, and inside that dome, basically it's called a saturation dome or a saturation curve. So inside that dome, the fluid is saturated, meaning it's a mixture of vapor and liquid that is, it's a mixture of vapor and liquid. So we've got, it can be of any concentration, and inside that dome we get interesting things like a constant temperature. So as you can see, the line of constant temperature goes vertical on the left, which we'll talk about in a second, and it's constant through the saturation dome. What that means is when we're boiling, this is something we all know. When we're boiling something, the temperature doesn't change. So when we're boiling CO2, for example, the temperature, as we transition from being 100% liquid to 100% vapor as we boil, that would be moving from left to right as we added energy on this diagram. The temperature doesn't change. So the inside this dome is saturated. On the left side of the dome, over here, on the left side of the dome is liquid. So as we go, for example, this line of constant temperature, if we were on the very left side of this dome here as 100% liquid, we would transition all the way to 100% vapor on the right-hand side of the dome. So the right-hand side of the dome is vapor, and as we get further and further away, we have superheated vapor and that. We have other information available on this chart. Some of them are very complicated, but two other ones that are interesting. We have constant density. We have constant entropy, which we use to talk about compressors and the isentropic efficiency of compressors. And we have the critical point. So the critical point is showing on this diagram at the top. It's always at the top of the curve. And the critical point is something that we don't talk about a lot with any other refrigerants, because we don't go near there. We can get there with certain refrigerants, ammonia and some other ones, but because we design our systems not to go above that point, we don't really talk about it very much. So the critical point for CO2 though is 31 Celsius and 73 bars. So 1070 psi and about 88 degrees Fahrenheit. And what happens above this point on this diagram is that you have a substance that's not a liquid or a vapor. It's a supercritical fluid, and it behaves differently. It behaves similar to a extremely dense, so a fluid that has like the density of liquid but behaves kind of like a vapor. And so the properties change up there. So why are these diagrams so useful? And the reason that they're so useful is that we can tell a lot of information about them by plotting out a very basic refrigeration cycle. So many of you will have done this before, but what we can see right away by looking at the differences in enthalpy is we can see the, in our evaporator, as we're boiling refrigerant away, we're doing work, we're absorbing energy. So inside the evaporator, the green section of this diagram here, we are obtaining refrigeration, which we call our net refrigerating effect. We have what's happening in our compressor. In our compressor, we're raising the pressure, so it's going vertical, and we're doing that at some sort of efficiency. So there's an increase in energy required, and in a perfect compressor, for example, would follow one of those lines of constant entropy. We don't have perfect compressors, so they go a little bit off that line, but that is the electrical work, or whatever, typically electrical, but it can be other things, the work that we're putting into our refrigeration system. And then we have the heat that we have to reject. So this is what's happening in our condenser as we reject the heat from our system before we turn this superheated vapor that comes out of our compressor, and we condense it back through the saturation dome back into a liquid before we put it back into our refrigeration and back into our evaporator again through a metering device. So that's a very basic, and I know it's rushed, but that's a very basic refrigeration cycle. And one of the reasons we use this diagram is precisely because it's easy to visualize this. So here we're visualizing the heat rejected, the net refrigerating effect, and work, which are, some of the very interesting things about the refrigeration cycle, and interesting parameters to understand how they relate to each other. For example, if you're looking for your COP, or your coefficient of performance, that's simply the effect you're getting divided by the energy you had to input. So in the case of a refrigeration system, it would be the net refrigerating effect divided by the work you put in, right? And that would be giving you your COP. So, just by looking at this diagram, it looks like on this particular one, the COP is something slightly over 2. In a heat pump application, your COP, you would be looking at your heat rejected. So you have, this is the heat that you're giving up. If you're able to use all of it, your COP would be that divided by the work that you put in, for example. So back to CO2. I guess back to the critical point. The one last thing on the critical point, which is up here, is just to give it one more description. It's basically, if you can imagine that one of the ways that we can turn one of the ways we can turn vapor into liquid is by squeezing it, right? If we keep adding pressure to a gas, we can eventually turn it into a liquid. And what the critical point is the point at which the pressure at which that's impossible. So above that line, we can squeeze it as much as we want, and it will never turn into a liquid. So one of the ways that we're going to start to use some language that's used in CO2 refrigeration in particular. One of the ways that we can control a CO2 refrigeration system is to make sure that we never go above that line. So going above the critical point would be operating in a region where we're supercritical. So if we stay below it, we're subcritical. So this is a really basic pressure enthalpy diagram here showing that. That system in the background is actually a subcritical CO2 system. And if you look really closely, right behind the pressure enthalpy diagram that I've got, you can see a similar pressure enthalpy diagram stickered onto the vessel there. So a subcritical system is a system that operates below the subcritical point. So I guess right away you should notice that this is a problem in the case of a warm climate like most of yours. You've got a 35 degrees Celsius or 40 degrees Celsius day, and the critical point is at 30. There's no way you could reject heat at a temperature this low, right? So subcritical systems are typically divided into two categories. They are into a cascade condensing and a volatile brine. So we'll talk about those two different kinds of subcritical systems. So cascade condensing, actually first we'll talk about volatile brine, but in both of these cases, what we're doing is using a secondary fluid to reject the heat outside. Instead of using CO2 transcritical, we're going into another refrigeration system, some sort of a cascade, so that we can use a refrigerant that is more efficient rejecting the heat outside, and we can force this CO2 portion of the refrigeration system to operate constantly subcritical. So why would we do that? Well, one of the reasons is safety. So one of the most common applications of the subcritical CO2 system is an ammonia CO2 cascade. And in an ammonia CO2 cascade, what we have is ammonia cooling the CO2 condenser in a temperature region that is very, very efficient for ammonia. And a CO2 is then used throughout a warehouse in order to actually provide the cooling to the spaces. So safety is one of the reasons we do this. We do it to keep ammonia out of for example, out of the cold storage or out of the distribution center, and to keep ammonia basically contained into a machine room and use CO2 out in the places that are occupied. Pumping power. So where I live, there's a lot of arenas and a lot of ice rinks, and we typically have used brines or glycols to refrigerate the concrete that we build ice on. We can also use CO2, and when we do that, we see probably a 4 or 5 times decrease in the size of the pump required, because we're boiling the CO2 in the pipes instead of just using heat transfer, sensible heat transfer. We can get away with moving a lot less fluid around, and we can have a lot smaller pumps. So if you're comparing, for example, glycol to CO2 as a secondary coolant, CO2 is going to use significantly less power. And efficiency. So one of the questions that comes up here is often when we talk about a volatile brine, and we'll look at this phase diagram in a second, is we're pumping CO2 around in a secondary system. Isn't that less efficient than just using the refrigerant in the first place? And on first glance, it would be, because we've got a heat exchange in the middle, right? We're using ammonia to cool CO2 down to below the critical point somewhere, so somewhere around 30 Fahrenheit or 0 Celsius, we're condensing CO2 at 0 Celsius, and then we're evaporating it at the same, I guess, if we're doing a pumped secondary. I'm going to get into some of that detail in a second here, but the truth is CO2 has some really interesting properties that actually make it more efficient in a heat transfer application, especially compared to a refrigerant like ammonia that's not dense. CO2 is very dense and it has very high pressures. So one of the things that happens, for example, comparing it to ammonia, when we're working with an ammonia evaporator, we can't handle pressure drop. We want very, very, very little pressure drop in our heat exchange surfaces, because all pressure drop in a suction line and in an evaporator ends up as a fairly significant increase in energy use at the compressor. With CO2, when we're operating, so for ammonia at 0 Celsius, we're operating at about 30 psi, or 2 times atmosphere. If we are doing that, a 1 psi pressure drop is a lot, but the same pressure with CO2 would be in the hundreds, and we could afford more, we can have more pressure drop. And because of that, we can take advantage of way smaller tubing in our heat exchange surface and heat exchangers and our evaporators. We can use the pressure drop to our advantage to increase the heat transfer of our heat transfer surfaces, like evaporators and condensers and gas coolers and the like. So there's some properties of CO2 that actually let us get back the efficiency of having to have a heat exchange inside our refrigeration process. And what I mean by that is, when we have an ammonia cooling the CO2, we have to run the ammonia colder than it would have needed to be if we had just put it directly into the space, for example. And that running that colder would lead to an inefficiency. So in a volatile brine, what you're seeing here in this pressure enthalpy diagram, so this is probably what I should have started with first, is the gray is, for example, the other refrigeration system. This is a bit of a leap, because the saturation dome would not look the same for 2 different refrigerants. But just to try to visualize what it would look like, you've got a refrigeration cycle in gray showing you the ammonia, or I've seen 134A Cascade with CO2, and it's a normal refrigeration system. It's running slightly colder, and then what you see in the green is basically pumped CO2. So the CO2 would leave the system. I believe I've got a slide showing a system. Actually, I'm not sure I do. The CO2 would be pumped out of a vessel, evaporate or partially evaporate in evaporators throughout the facility, and then it would come back into that vessel and condense. So there's no compression. So this works really well for medium temperature applications like coolers, like distribution centers, coolers, and things like that. It doesn't work that good. It works the best when we are taking advantage of the efficiency of the primary refrigerant. So if we're doing this in an application where the gray here on this diagram is ammonia, and we're running it at an area where ammonia is very efficient, then this works really, really well. So it turns out that leads itself to medium temperature applications. If we have to go colder in a subcritical system with CO2, we have to use compression. So this diagram looks similar. We've got the same gray refrigeration system going on there, which is the ammonia or 134A or whatever we're using as the primary or high side refrigerant. And we've got a second refrigeration cycle happening at a lower temperature. So here you've got the red compression. The blue is the heat rejection of the CO2. It's going through a metering device, and then it's being used in a cold evaporator. The PNID that you can barely see behind this is a drawing of a cascade condensing minus 50, I think, freeze dryer CO2 system. So this works really well when you need cold. CO2 works fairly well down to minus 55, and it can be fairly efficient. So these systems are much more efficient, but they're more complicated. Sorry, much more efficient. They're much more efficient at cold temperatures than, say, doing volatile brine, or even in some cases just using ammonia. Now, this type of system is much more complicated than the one we looked at first, because we have compression happening. And if we have compression happening, we have oil. And managing oil in a CO2 refrigeration system is different, especially a cold one like this is different than a typical refrigeration system, because if you notice here, nothing is ever getting that warm. And we actually have to do things like, instead of oil coolers in reciprocating compressors, sometimes we have to use oil heaters to make sure the oil stays warm in the crankcase. So there's some challenges to this. We've now got oil out in the CO2 that we need to separate, and things like that. So it's not simple, but this is what can be done, and is being applied to things like ice cream and different types of production facilities that are operating at really low temperatures. The other option we have is to, instead of doing something subcritical, instead of using another refrigeration system to keep the condensing temperature of the CO2 low enough that we stay in the saturation dome, we can do what we don't do with any other refrigerants, and we can just let it go. And we can run it in a supercritical region. And so many of you will have heard the term transcritical, and transcritical means a system that has the ability to switch between being supercritical and subcritical. It's operating in both regions. And so a lot of these systems will operate supercritically when they need to, but then transcritically when they can't, or sorry, subcritically when they can. And so that's where the word transcritical comes from. So supercritical fluids, our supercritical refrigeration cycle looks like this. We're going to look in detail about some of the efficiencies of this and some of the advantages of this, or disadvantages, if you will, in a moment. But basically, the same thing is happening, but instead of condensing up here, the blue line at the top, there's no condensing happening here. This is transitioning from a warm superheated vapor at the top of the red line to a subcritical fluid, or maybe even supercritical fluid, maybe even a supercritical fluid there, and it's just cooling off. It's moving through lines of temperature, and we're going to look at that in a different diagram momentarily. So instead of having a condenser, what we have is a gas cooler, and that's the way. So that's where the terminology gas cooler comes from in a supercritical CO2 refrigeration system. So one of the things that happens here is that I'm being fairly generous on this diagram on the length of that blue line, and we'll look in detail here momentarily, but these systems are not very efficient, and they're especially not very efficient when you have to operate them when it's warm. So just to give you a bit of flavor, this diagram shows you the approximate COP of 6 different refrigerants. And this is showing you, there's a lot of assumptions built into this, but it's basically what it's like a walk-in cooler operating transcritically, or supercritically, sorry, at about -4 evaporating and +30 outdoor air temperature. And this is showing you the COP of these different refrigeration systems. Now, bear with me, I did this on purpose because there's a lot of, at least in where I am, there's a lot of talk about how efficient CO2 is, and I want to kind of put a reality check on some of that stuff and have a discussion about why we can say that and when we can say that. So this is just doing a straight comparison with a typical refrigeration cycle on these 6 different refrigerants. What happens with CO2 is there's some things we can do to make it better that we can't easily take advantage of in other refrigerants, similar to what I mentioned earlier about the pressure drop in heat exchangers, and we can change these numbers a bit and get it better. But just at a first glance, CO2 is not very efficient in this application. So again, this is about a -4 evaporator in a 30-degree outdoor ambient temperature. As expected, ammonia and CO2 are the most efficient. They're both very, very, very good refrigerants at this temperature. 410A is a little bit worse, and 1234YF is there in a similar place. So we're going to talk about how we can get CO2 to be more efficient in a minute. But one really cool thing happens. This is the part. This is the part of the presentation where I try to get a little too excited. This is something I've been in refrigeration for a long time, and it still surprises me a little bit how excited I get and how interesting I find the stuff that happens when we are dealing with refrigerants and things that we can do. And this is one of those cases. So one very, very interesting thing happens when we talk about operating a refrigeration system CO2 trends in a supercritical realm. And before I go there, I'm just going to go back to the general refrigeration pressure enthalpy diagram. So here you can envision here, if I increase the amount of work I'm doing, if I increase where this blue line is, if I make that higher, meaning that I have to reject heat at a higher temperature because it's hot outside. If that line goes higher, I'm actually going to end up getting less net refrigerating effect, and I'm going to have to put in more work, right? So this is common understanding, as we increase the compression ratio, or the lift, some people call it, of the refrigeration system, we decrease the energy efficiency, right? So that's where CO2 has some pretty interesting characteristics when it runs in the transcritical region. So in the transcritical region, because we're not dealing with lines of constant temperature that are horizontal, because like we are in the saturation dome, we have the ability to increase the pressure and increase the amount of work by some small amount and get a large increase in net refrigerating effect. And that's because the lines of constant temperature above the saturation dome come down on a curve similar to that purple one, meaning that as we transition from right to left, as we reject heat, we are no longer condensing, we're rejecting heat along a continuum, a gradient of temperature change. What that means is we can go as far left as the outdoor air temperature, or something slightly above the outdoor air temperature. This is where CO2 has a big advantage in cold climates, and we'll talk about that. So this is in a normal climate, we can get an efficiency gain like this. But what does this mean? This means that we don't want to just minimize the compression ratio like we would on a normal refrigeration system. We need to control it to some optimum, and that optimum is somewhere usually around 1400 psi, but it depends on the outdoor air temperature and the saturated suction temperature. So this adds complexity to control, right? We have to control this now, and you can see, just looking at this diagram, that if the controls aren't working properly, you can see a massive change in COP. And one experience that I'm familiar with on a cold storage warehouse experienced just this. They had set up a couple of different CO2 systems to do this cold storage, and the control system on the one wasn't working quite properly, hadn't been commissioned and tuned properly, and basically it was using twice the energy of the other one. And so we can see applications where that happens, and why it's so, and why this adds complexity and challenges in commissioning and in startup. What's cool, if you live in a cooler climate, is you can even take more advantage of this. So for example, you can keep getting it colder and colder and colder and get extremely way more net refrigerating effect for very small increases in work. And this is how the arena's set up to do it often, so that we can get very, very efficient and still have some heat recovery, which we're going to talk about heat recovery next. So I find this fascinating, but it adds a level of complexity to the control of the refrigeration system and to its operation in supercritical state. That is a challenge, right? And it adds to drift over time as you commission systems. They don't usually stay that way. When we look at an industrial ammonia system, we use hand expansion valves and things that are very robust from a reliability perspective. Here we have to have a lot of electronic controls and a lot of algorithms to understand what we're doing and different stuff. So it adds some challenges. So in heat pumps, CO2 has another, the same property that we're just talking about with operating in the supercritical region, is actually very, very beneficial to heat pumps. So the first thing is, the same thing happens where a little bit of work increase leads to a lot more heat rejection. So that's fine, and that's very, very good. But more importantly, the lines of temperature up here are not straight, are not horizontal, which we talked about. What that means, though, is that, let's say your discharge temperature is 300 degrees Fahrenheit. In a typical refrigeration system, if we were down operating below the saturation dome, 350 is maybe a bit high. We compress to 200 degrees Fahrenheit, so 100 100 Celsius, and we reject heat down to our condensing temperature, which might be 35 or 40 Celsius. Once we hit this dome, so envision a line, the system operating in a subcritical realm, we compress it up to 200 degrees Fahrenheit, 100 degrees Celsius, and we reject the heat down to about 40 Celsius. That's a small amount of the total energy that we're rejecting, right? The rest of the heat is rejecting to transition the phase, to do a phase change from vapor to liquid, and that's all happening at the same temperature, which is, whatever, 35, 40, 45 Celsius. That is not a warm temperature. So if you're into heat recovery applications for domestic hot water or something like that, you can only get a small portion of the heat, and it usually is around 20%, 25%, it depends on the system. But around 25% of the energy you can get back at a warm temperature, at a gradient between whatever it came out of the compressor at, say 100 down to 35. But with CO2, it's a gradient all the way. So if this purple line was 85 Fahrenheit, 30 Celsius, then as we went from 100 or 120 all the way down to 30, we'd be going through a gradient of temperature change. And what that means is with a counterflow heat exchanger, we can get temperatures of our water or whatever we're trying to recover. We can use all of the energy and get temperatures up to something close to our discharge temperature, which means we can heat domestic hot water, right, to 60 Celsius or whatever. Sorry, not 60 Celsius. Yeah, about this is 140 Fahrenheit, whatever that is. So it means we can heat domestic hot water, we can heat cleaning water for production facilities, we can do lots of different stuff on the heat recovery spectrum and remove this energy. So what some applications do is they'll split this whole top dotted blue line here into several different stages of heat recovery. They'll have 3 or 4 different heat exchangers. So if we worked with 3, they'll have the first heat exchanger that takes all of the high grade heat and does domestic hot water, something that we need really hot water for. It'll take the next phase to do things like air handler heating and different stuff like that. And it'll take the last bit of warm water to do underfloor heating and heating sidewalks if they need to, but underfloor heat and other low temperature applications, or preheating boiler feed water or something like that. So we can take advantage of all of the energy of recovery a lot easier than we can when we are condensing. So I already talked about transcritical, and basically that's a system. The system in this picture is a transcritical CO2 rack, grocery store style system, and it's a system that is able to switch between the 2 modes of operation depending on what offers the highest efficiency benefits and gains. So this is the same conditions as that graph before, except operating at a 10 Celsius outdoor air temperature. So that's cool, but if we had that, the COP of CO2 is all of a sudden significantly better than a lot of the other refrigerants. Now, many of you will have seen this chart before or something like this. This comes out of the IAR CO2 handbook, but there's several versions of this around. And it shows kind of the areas where transcritical is better than subcritical. And this is an older version of it, because what keeps happening is because of technology gains, those lines keep coming closer and closer together. I'm aware of transcritical CO2 units being effectively used in the southern US in warm climates. So these lines are moving closer and closer together. But in order to do so, what they're doing is invoking basically technology, where we're looking for technological things we can do to improve the efficiency of a CO2 system. So I'm just going to talk about a couple things, but there's a few different things out there. Some of the stuff is still in, I don't know, I don't want to say research stage, because there's applications that's being used, but some more applicably than others. So the first thing is using parallel compression, and and what they're, and ejectors. So if you're familiar with ejectors at all, they basically use high pressure vapor to entrain a lower pressure fluid and compress it. Kind of like a paint gun uses air to entrain liquid. It's similar to that. And in CO2, it turns out we have this very big pressure drop we need to deal with coming out of our gas cooler at over 1,000 psi. And we need to get it down to 400, and we have this very big pressure drop. So what we can do is actually use that to entrain vapor and get essentially free compression. So this is becoming more and more common in rack style systems. One of the manufacturers makes a multi-port injector. Some make adjustable ejectors. So this is an area of continued development, but in doing so, we're taking advantage of the properties of CO2 and increasing the energy efficiency. This is what a multi-port injector looks like. So they've got high pressure gas coming in, and they'll choose to open several different ejectors depending on the system parameters at the time, and then it will entrain. It creates a low pressure region as it flows through the nozzle, and that will suck in the medium temperature pressure and help compress it to where it goes to the receiver. So these are functioning very well. The other thing that is being used is several different types of basically of turbines. As you decrease the pressure in something, typically we've used like expansion valves, which are an isenthalpic device essentially. So there's no change in enthalpy as you decrease the pressure. That's why if you look at all the diagrams that I've shown you so far, this left line here is always straight. But if you put it through some sort of a turbine device, you can actually get that line to follow lines of, or something similar to a line of constant entropy, which is going to be more of an angle to the left, and you can end up getting work out. And the challenge there is what you do with that work and different things like that. But there are applications in demonstration that are using technology like that. So that's one of the reasons you start seeing CO2 applied more and more and more to hot regions, is this increase in technology and increase in efficiency at high temperatures. So this is just a picture of a CO2 heat pump that was installed in, I believe, a dorm in Canada, in Montreal. I'm not actually sure about Montreal, in Quebec anyways. And this is one of the manufacturers makes these CO2 heat pumps that provide chilled water and hot water, right? This is similar installation. Actually, that other picture might not have been in that dorm. This is the one that's in that dormitory, I believe. One of the common applications that we're seeing in a lot of jurisdictions, especially ones where energy efficiency is really important and a move away and decarbonization is important, to move away from fossil fuels, is heat pump water heaters. And you can buy heat pump water heaters, at least here, you can buy them with R507 right now, or R404A refrigerant in them. They're quite expensive, but and they don't, they work okay. CO2 hot water heaters, as we showed with the heat recovery portion of the slides, CO2 hot water heaters are more, can generate warmer water and can function fairly well. So they're gaining in popularity. They do have some trouble in warm climates, so they look for some technology improvements there. Safety. So one of the things that comes up, I always want to spend, this is the last slide, I want to spend a few minutes talking about safety of CO2 systems. One of the things that I hear a lot is that CO2 isn't toxic, and that's not true. When you breathe in oxygen, you're breathing out CO2. Your body does not want an overabundance of CO2. You can die from CO2 poisoning. When ASHRAE rates refrigerants, I don't know if all of you are familiar with the rating scale, but for toxicity, there's 2 letters, an A or a B. And a refrigerant, if it has a occupational exposure limit of lower than 400 parts per million, meaning that you can only handle less than 400 parts per million over an 8-hour period exposed, it gets a B. meaning it gets called toxic. If it's above 400, it gets A, meaning it gets called low toxicity. It's a simple cutoff. So CO2 is fairly high, but it still is not non-toxic. And that's very important to think about when you look at refrigeration system design. One of the things we have to do is make sure that if all of the refrigerant charge leaked into the smallest space, it's called the refrigerant concentration limit calculation. If all of the refrigerant leaked into the smallest space, would that space become toxic to the people, to the occupants in that space? And the thing with CO2 is it actually ends up being, in large systems, it ends up being fairly easy to get there. The other thing is it has high internal energies and pressures. So when things happen, I don't share a lot of the pictures because they're given in confidence, of course, but there's several pictures out there and several systems where pipes have ruptured. And a lot of that has to do with materials control. So because CO2 can use copper and stainless tubing, and often, especially on the low sides of the system, the 450 PSI range, copper is an effective material and is used quite commonly. We don't have a lot of good control on materials, especially in commercial installations. And so if we just use regular type L copper or K copper, type L, typically type L copper, then we apply it to the wrong applications, especially larger piping, we actually exceed the limits of the materials. And obviously it's not a proper design, but it does get done because we don't control materials in commercial projects quite the same as we do in industrial work, at least in my experience. Safety reliefs offer an interesting challenge. So I showed you earlier, so the picture you see here is an opened up dryer core I found on the internet. I had some different pictures, but anyways, this one has solid CO2 in it. So when you have a safety relief scenario, if your relief is happening from a place in the system where the vapor could be close to saturated or it's liquid, you can end up going straight to solid. And there's some concern that this would block relief piping. That would be very bad, right? So a lot of applications, we are doing things like limiting the piping on a relief valve outlet, meaning we try to do no piping on the outlet, which means the valves have to be outside, which means inlet relief piping. That leads to a whole bunch of challenges because inlet pressure drop on relief valves, if you have too much inlet pressure drop, can lead to valve chatter and different stuff like that. So there's a lot of nuance in designing an overpressure protection system and safety relief system for CO2. Another challenge is ammonia CO2. So I talked about ammonia CO2 cascades being really good, but when you mix ammonia and CO2, so if the heat exchanger fails and you mix, it generates a substance called ammonium bicarbonate or ammonium carbamate. Yeah, just ammonium carbamate, and it's a white powder. And of course, because CO2 is higher pressure than the ammonia, it leaks into the ammonia, and all this ammonium carbamate gets all over the ammonia system, and it's very bad and very, very, very difficult to clean up. So there are systems for detection and isolation that we can employ to prevent that, but there have been incidences where this has happened. Standstill pressure. So it's getting better now with more and more materials, but even still, if you don't design the low side of the system to handle very high pressures, then the system can't handle a power failure without overpressure. So because of course, as the system warms up, the pressure is going to go up to potentially 1,000 or more PSI. And so there's several different methods to employ it in order to handle this. Something like a fadeaway vessel, a large vessel that can absorb it. There's one of the more common applications is to use a very small little generator run refrigeration system to keep one vessel cold. That way the CO2 pressure never gets high enough. And the other way is just to let it go. So in places with fairly reliable power and fairly cheap CO2, which CO2 generally is fairly cheap, you just let it go and charge it again. So while it sounds easy, that still costs money and is still a pain and still a loss of refrigeration. And the other thing is really high coefficients of liquid and vapor thermal expansion. So again, unlike other refrigerants, another kind of interesting property of CO2 is that the vapor thermal expansion coefficient is not insignificant, meaning that when you trap cold vapor and let it expand, the pressure can grow. So, for example, roughly a 15 degrees Celsius rise in, about a 10 degrees Celsius rise in temperature. About a 15 to 20 degree rise in temperature can result in about 100 and basically a 1 or just over 1 bar temperature rise. Sorry, I'll get that, my units are wrong there. 55 degree Fahrenheit increase, I was trying to do it on the fly and I didn't do a good job. 55 degree Fahrenheit increase and 120 PSI, right? So that's not that much, but it's 120 PSI of rise in pressure just from a small warm up of a vapor line. So we always have to worry about liquid. In all refrigerants, we worry about trapping cold liquid because trapping cold liquid is like creating a bomb. But we don't typically have to worry about trapping cold vapor, and with CO2 we do. We have to give it some thought. And even with liquid, of course, it's higher. So we have to be cautious. So there's a lot of safety related aspects of CO2 design to consider. Nonetheless, it's being applied in a lot of applications with a lot of success. There's a lot of benefits to it. There's a lot of reasons to do it, a lot of reasons to use it as a refrigerant from an environmental standpoint. Very low global warming. It's very safe from an occupant point of view, especially if we're comparing it to ammonia. And so I think the applications are going to continue to increase. The technology is improving all of the time. We're going to start seeing more and more hot weather applications of transcritical CO2 systems, and it's as we transition for one more refrigerant change again away from HFCs, we are seeing more and more people interested in natural refrigerants, and this is obviously one of those, and has a lot of benefits, but it does come with drawbacks, and those need to be considered, especially on the safety side, and especially on the complexity of operation and energy efficiency. So that's all I've got from a presentation perspective. I'm not sure how the format for you guys functions with questions, but I'll leave it open for any questions. So I know the presentation was a bit of a high level overview, but I wanted to give everybody a flavor for how CO2 works, why we're talking about it, what some of the challenges are, and where it's being used successfully. So
thank you, Mr. Wade, for such a thoughtful presentation. We have got some questions from the participants. Yeah, what is the price comparison between an efficient Freon and CO2 system?
Okay, sorry, what's the price
comparison between an efficient Freon and CO2 system?
The energy efficiency, or just the cost? Sorry.
A cost.
Okay, so the cost of an install. So the CO2 should be the same or very, very similar. Right now, in my experience, at least, they're not. CO2 is more expensive because a lot of the components are more expensive, but CO2 uses significantly smaller piping. So when you compare it with an ammonia or a Freon type system, CO2 will have pipe sizes that are significantly smaller. So the installation cost should end up being lower. We're not seeing that just yet, at least in my experience. We're seeing a little bit increase, probably about a 15 to 20% installation cost premium to put in CO2 at the moment, but theoretically they should be very similar.
And next question is, would you like to prefer the CO2 system when the temperature is greater than 30 degrees centigrade?
Would I use one then?
Would you like to recommend the CO2 refrigeration system where the temperature is greater than 30 degrees centigrade?
Yeah, I think a lot of that depends on if you're using a really good system that has the top of the line technology, you can successfully operate in those temperatures. A lot of it depends on whether that's for a short period of time or all of the time. So as you saw in a couple of the graphs, the efficiency of CO2 increases quite a lot as it gets cooler. So it depends a little bit on the whole kind of like annual weather cycle of the place, whether it would be ideal or not. So if it's always 30 degrees Celsius, then if it's always 30 degrees and it's not cool in the evenings or at night or anything like that, then it's going to be harder and harder to employ the technology as in a CO2 transcritical type system unless you need the heat for some reason. So if you need the heat for some reason, or you have a range of temperature, so it's only operating at 30 above 30 for 2 or 3 months of the year, but the other 7 or 8 months are, and if I could do math, the other 9 months are cooler, then those things would factor into that kind of decision. So it's not, you can't just make one kind of recommendation. Like I said, I know, for example, Atlanta, Georgia has several operating CO2 refrigeration systems, or well, at least 2, and it's very, very hot there and hot and humid in the summertime. So, and they claim that the efficiency is there, but you have to use technology like ejectors and all of that kind of stuff to improve the efficiency, and then you have to take advantage of heat recovery if you can. So I know I didn't quite say yes I would or no I wouldn't, but those are the things you'd have to consider. You have to consider the annual weather and everything like that.
The last question today's session: how do you deal with the phase change from vapor to solid in an operating CO2 system?
Okay, so you should never, it shouldn't happen in an operating system, because if it did, you would be at minus 70 Fahrenheit, so minus whatever that is, minus 60. But it only happens in the result of a depressurization. So it only happens when there's been a leak typically, or when you're letting the refrigerant out or something. And the way you deal with it is easy. I mean, the system stops operating mainly, especially because there's been a leak or you've depressurized for some reason. But basically, all you need to do is increase the pressure. So as you pressurize it, as you transition above 76 psi, everything that turned into vapor everything that turns solid will turn back into either liquid or vapor, depending on the temperatures. So it's just a slow repressurization will take care of that, and there's some service related issues there, like not creating a lot of large pressure behind a blockage or something like that. But in general, it's quite simple, a case of just increasing the pressure. Unlike water, of course, CO2 doesn't expand when it turns solid, so it shrinks when it turns solid. Like most substances, it's not like water, so it's not going to burst the pipes or anything like that. Is there any other questions? I don't know if anybody's talking. I can't hear you.
Hello.
Hello.
Actually, my connection was lost. So thanks, Mr. Greg, for such a thoughtful presentation. Okay, I would also like to thank all the participants who have attended the presentations and benefited. I would also like to thank to Mr. Rishabh Kasliwal, President, Asia Rajasthan Chapter, Mr. Nishant Gupta, President, Western India Chapter, and Mr. Amarjeet Singh, President, Chandigarh Chapter, for supporting us. Once again, thanks to all the participants, the speakers, and once again, thanks to Mr. Greg. It was really a nice presentation.
What's that?
Yeah, it was really a nice presentation. CO2
Okay, thank you. Yeah, thank you.
So in near
hope
future, in near future we can have some more presentations as per your capabilities.
Yeah.
So I am ending this webinar. So thank you once again. Have a nice day.
Yep. Thank you. We'll it was a pleasure, and I appreciate the opportunity. We'll talk soon.